for learning algorithm to tune their hyperparameters. Of course, for this kind of scenario, there is no model, but the data-driven method had very good performance. But on the other hand, even now we have very good success in the application of learning. But on the other hand, our understanding or our knowledge about the learning lays behind the development of learning. Many learning algorithms behave as a black box, so they achieve very good empirical performance, but their mechanisms are very difficult to interpret or analysis. So based on these advantages and the disadvantages of the two disciplines, so my perspective is that how can control benefit learning, and vice versa, how can learning benefit control? On the one hand, right, so we have different kinds of ideas in control theory. Can these ideas or can these well-established tools be applied to learning or to better understanding the learning algorithm? And on the other hand, as I mentioned, even in the learning field, even without a model, we can have a very good performance. Can we bring this idea to control and propose some data-driven solution to the controller design, right? For example, even without model, can we directly learn from data the best controller? So that's another direction of from learning to control. So I have based on, within this intersection, I have done some work. So the first direction is control for learning. Of course, like for control for learning, different people may have different ideas, different perspective. So from my perspective, I think control is a very good tool to analyze the robustness of learning algorithm. So usually, learning algorithm depends on data, right? So usually data is noisy. How can learning algorithm perform under the influence of noisy data, right? So the learning algorithm should degrade elegantly in the face of perturbation, or in other words, that's the purpose of robustness of learning algorithm. So in this direction, so we propose a framework under the input to state stability, and based on this framework, we study the robustness of policy optimization algorithm and even the adversarial reinforcement learning algorithm. And in the other direction is learning for control. As I mentioned, reinforcement learning, especially reinforcement learning algorithm, can help us directly learn from data the optimal controller, right? So this controller not only should be optimal, but also should be stable, right? So in this direction, I propose some algorithms for the time delay system and for the output feedback systems. And in terms of applications, I have some applications of data-driven control in well-like robots, autonomous driving, and we also use reinforcement learning algorithm to explain the computational neuroscience, or propose some ideas in computational neuroscience in terms of human motor systems. Okay, so today let's begin the first part of today's talk. So the first one is control for learning. So here, as I mentioned, we propose some ideas based on input to state stability to analyze the robustness of learning algorithms. So today's this talk is basically based on these three papers. And this is a collaborative work with my PhD advisor, Zhongping Jiang, and Eduardo Sontag, and also with my postdoc advisor, Richard Bratz. Okay, so as I mentioned, I wanted to study the learning algorithm, right? The behavior of learning algorithm. But like in machine learning, there are so many different kinds of learning algorithms. So where should we start, right? So I think even though there are various learning algorithms, but the fundamental solution is optimization, right? Even for the classic learning algorithm, for example, classification, regression, or even later for reinforcement learning algorithm, supervised learning, or even unsupervised learning, they are all from an optimization algorithm, right? For example, for the backpropagation of the deep neural network, we should use the gradient-based algorithm to solve the optimization problem. So therefore, we aim to study the following optimization problem. So J is our loss function or objective function, and D is the domain of this objective function, and k is the decision variable. We want to find the k such that the j is minimized. Of course, this problem is typically non-convex, right? Of course, if it is convex, we have very good property, but generally, this function is non-convex. And to solve this problem, we have very simple and very useful algorithm to find the optimal solution iteratively. So that's the gradient-based method. So gradient-based methods are very powerful, but very simple, right? At each step, we just should move along the gradient descent direction. And by this way, we can ensure that the cost or the loss function can be minimized iteratively. Okay. Or if from here, we can see that if eta is super small, step size is very small. So this kind of gradient descent algorithm can be interpreted as a ruler discretization of the following gradient flow, right? So this is the ODE system. We can see that this system, the discrete time system, actually this discretization, directly discretization of this continuous ODE system. We call this equation as the gradient flow. Okay. As we know, if under the assumption of existing of the global minimum, so this is the assumption of the existence of minimum, global minimum. And if the global minimum exists, and we find that the relative loss, this is relative loss, is directly the distance or difference between the cost function and the minimum value, right? So we find that if we take the duality of this equation, we find that it satisfies this kind of property, right? Which means that when moving along the gradient descent direction, the relative loss is strictly decreasing, right? And finally, it will converge to the critical set by Lassalle's invariance principle. So what is the critical set? So here we define critical set at all the points where the gradient should be equal to 0. That's a gradient, that's a critical set. Oh, sorry, here I have a typo. Of course, the target set should be contained in the critical set. So here should be, there is a typo. So the target set is the set of all the global minimizers, right? Actually, we wanted to find the global minimizers, but due to the limitations of the gradient-based method, usually we can only converge to the critical set, or where the points where the gradient should be equal to 0, right? Okay, so that's some basic introductions of the gradient-based method, right? Okay, but now in machine learning, usually, like gradient can't be directly computed. We have to use other kind of algorithm to estimate the gradient, right? For example, at this left-hand side, this is the gradient-based algorithm. And right-hand side, there are some gradient estimation algorithm, or we call it oracle. At each time or at each step, the gradient-based math algorithm should query about the gradient at position k, and then gradient estimation will provide a estimated gradient to the gradient-based algorithm, and then we can move k to the new direction, right? That's the whole workflow of the gradient-based algorithm. But here, as I mentioned, for this part, it is usually should be implemented by our algorithm. For example, there may be some oracle, right? There are some oracle. You ask your oracle, and oracle will give us some estimation. Or maybe it is a digital twin, right? So we can ask a digital twin about the estimation of the gradient, and then it will tell us the results. Or maybe in this part, there are some data, right? So even though we don't know the model, we can't get the estimation, we can't get the exact gradient, but there are some data would help us to calculate the gradient. So in a word, so in machine learning, usually gradient should be estimated by some algorithm. Because it is an estimated result, of course, there must be some errors, right? For example, if data is noisy, there must be some noisy introduced or perturbation introduced by the noisy data, right? Or maybe in the gradient estimation part, there are some computational errors, right? Or maybe there are some adversary attacks in the gradient estimation part. Or maybe there are some model mismatch or inaccurate digital twin, which will result in the inexact gradient estimation. Or maybe there are some early stopping problem of gradient estimation process, right? So if this kind of scenario happens, there will be a noise that introduced to this gradient-based method, right? So in our word, in reality, this is the left-hand side is the ideal case, right? We can assume that it moves along the gradient descent direction all the time. But on the right-hand side, that's a practical scenario. In practice, the gradient-based algorithm is always like implemented under the perturbation. Here I use delta to denote the perturbation. The key question is how, so as I mentioned in the last slide, if there is no perturbation, the gradient flow will converge to the critical point, or even target point under some more strong consumptions. But under the influence of perturbation, the key question is how can we ensure that the gradient-based algorithm still performs very good under the perturbation? Or in other words, is the algorithm robust to such different kinds of perturbations? So that's the problem we're going to show in this talk. So in other words, we're going to show the robustness of gradient-based algorithm under the different kinds of perturbation. Okay, so that's problem we're going to show. So actually, this problem is not new, and it is started by several researchers. So here I list two classic or two very excellent or brilliant work, and there are of course many following up works based on these two ideas. So the first work is done by Polyak in his textbook. Okay, so in this book, in this work, Polyak suggests that if JK, if the cos function is strongly convex, under this assumption, the gradient descent algorithm will finally converge to a neighborhood of the optimality. So K star is the minimum. We can see that when K goes to infinity, the gradient descent algorithm will converge to the minimum, but under the influence of noise, it will converge to a neighborhood of the optimality. Here we can see epsilon is the magnitude of noise or of the perturbation, and rho is some function that converges to 0 as epsilon converges to 0, right? So this is a very good result, but it should assume that the cos function should be strongly convex. But usually, as we know, in practical problem, strong convexity is very hard to satisfy, right? And later I will come back to this equation again, and I will show that this kind of equation is actually the input to state stability. It ensures both the stable stability of the learning of the gradient-based algorithm and the robustness. So that's the input to state stability, which I will talk about it later. Okay. So that's the first work done by Polyak. Okay. So next, of course, there are many other brilliant works. So second work is done by Bersakas and Sissiklis in around 2000. Okay. So in their work, they assume that the noise should converge to 0, right? As we can see, eta is the step size. So they should assume that the step size should converge to 0. If step size converges to 0 based on this equation, we find that the perturbation should also converge to 0, right? So in their work, if the perturbation converges to 0, they can also ensure that the gradient converges 0 too. Okay, so that's another work. But here the limitation is that they should assume the convergent noise, right? We can see here it should assume the convergent noise. But in these two fields, the first assumption is the strongly convexity, right? But in many practical problems, many optimization problems are non-convex, not alone, strongly convex. So for example, here I will give you an example. For example, in the policy optimization for the linear quadratic regulator problem. So here we wanted to optimize the feedback in K. So the set of stabilizing controller or the set of demonstrable set or the feasible set is non-convex. So look at this figure. You'll find that the blue region is the feasible set and the yellow one is the non-stabilizing or non-feasible set. So we can see that the feasible set is the non-convex, right? And therefore, this kind of problem is non-convex. And secondly, in data-driven control, the assumption of vanishing noise is often unrealistic. So it's hard to say that after long time later, the noise will tend to zero, the noise will vanish. Because from our understanding, noise would be there all the time, right? So of course, this kind of assumption would be too strong to be satisfied by the real scenarios. So how can we propose some new ideas to solve this problem? Right? How can we propose some new ideas to study the gradient descent algorithm under the influence of noise? Okay, so the first technique we introduced is the input to state stability to quantify robustness, right? So robustness is kind of property, right? A quality property, but how can we quantify it? So here we use the input to state stability. I think if you I think because I'm a control researcher. So the first idea I learned, or the first concept I learned in control is the Lyapunov stability, right? Lyapunov stability tells us that okay, for any dynamical system without noise, so here without input, right? There is a zero input. And if my Lyapunov function is a negative definite, I can ensure that the trajectory of this dynamical system would converge to zero. Or in other words, it is asymptotically stable, right? That's the classic Lyapunov stability. But as I mentioned, we wanted to study the behavior of gradient-based method under the perturbation, right? But the classic Lyapunov stability only ensures the asymptotic stable under the zero inputs or under zero disturbance. But on the other hand, for the input to state stability, it can both consider it can incorporate the influence of the noise. So here in the right-hand side, W is non-zero input or non-zero disturbances. Okay, for input to state stability, it still have a similarly dissipivity like Lyapunov condition. So in order to ensure input to state stability, still we should ensure that the derivative of the Lyapunov function should be like a smaller, should be negative, or more strongly, it should be smaller than a k infinity function. But under the influence of noise, we should have additional term. So this one quantifies the influence of the noise. So under this condition, we can ensure both the asymptotic stable and robustness. So in this equation, we can see that when t goes to infinite, so this term will tend to zero, which means that our system is stable or asymptotically stable. And this term characterizes the robustness, which means that under the influence of noise, the trajectory will never converge to the equilibrium, but it will converge to a neighborhood of the equilibrium. So this is we can see like this region is the neighborhood of equilibrium, and the size of this neighborhood depends on the magnitude of noise, right? The larger the noise, the larger the size of this neighborhood. So that's why we should use the input to state stability to quantify the robustness of the gradient-based algorithm. Okay. And the second technique we use is to generalizing the classic Polyak-Łojasiewicz condition. Actually, Polyak-Łojasiewicz condition or PL condition was proposed in around 1963, and it is used to guarantee the convergence rate of the gradient algorithm of the gradient-based algorithm. So basically, PL condition or like some people would like to call it the gradient domination condition. So here we can see that the gradient will dominate the relative loss function. This is like this x-axis is the relative loss function, and y-axis is the gradient, right? We can see that the gradient is larger than the relative loss function by a linear function. Here, alpha is some constant. So if this kind of PL condition holds, so we can easily derive that, okay, our relative loss function will converge to the optimality exponentially. But if we can move a step further, we'll find that if this kind of linear Polyak-Łojasiewicz condition holds, then the gradient descent algorithm is an exponential input to stay stable. So here we can see that without noise, in this equation, we can see that without noise, the algorithm will converge to the optimality exponentially. But with noise, it will never converge to the equilibrium or to the optimality, but converge to some neighborhood of the optimality, right? So here, gamma determines the size of our neighborhood, right? Okay, so this can be easily proved by using this as the Lyapunov equation. Okay, so here I wanted to mention that if the strongly actually PL condition is a weaker condition than the strongly convexity. So if a strongly convexity condition is satisfied, it will directly imply the PL condition. Okay, but here another thing emerges. So here we can see that the classic PL condition should require that the gradient is larger than the optimality, larger than the relative loss by a linear function, right? But as we know, like in reality, linear rarely happens, right? Because linear function usually is an idealization of our research of our human. But in reality, most properties of most things are nonlinear, right? So therefore, the question is how can we generalize the PL condition such that it can fit more broader kinds of problems, right? So that's the motivation of K infinity PL condition. So based on the PL condition, we generalize to the K infinity PL condition. Okay, so here we can see that it's still the same equation, but here we only assume that alpha is a K infinity function. So which implies that this alpha function is strictly increasing 0 and 0 and tends to infinity. Okay, so that's this kind of K infinity PL condition. Actually, it is a weaker condition of the linear PL condition, right? So we can see in this figure, it is not a linear function anymore, right? Of course, if alpha is a linear function, it will imply it is a K infinity PL condition, right? Therefore, K infinity PL condition is a generalization of the linear PL condition to the nonlinear version. Okay. So if this kind of PL condition is satisfied by the cos function, then we can ensure the input to the stability of the gradient flow. So in other words, we can see that without the noise, the learning or the gradient-based algorithm is asymptotically stable. But under the influence of noise, it will still converge to a neighborhood of the optimality. Of course, the size of the neighborhood depends on the magnitude of the noise, right? That's the robustness analysis under the K infinity function. Okay, of course, this kind of conclusion can be developed by ISS Lyapunov function. If we choose V as ISS Lyapunov function, we'll find that it will reach the ISS dissipativity form, right? Okay, and then we can prove that it is input to stay stable. Okay, so now we can say that in this figure, yeah, even though now it is a nonlinear function, but we still require that it is monotonically increasing and tends to infinity when the relative loss tends to infinity. Okay, so that's another very strong requirement. but usually this kind of condition still can't be satisfied. So here I will give an example to show that the developed K-infinity PL condition is still too strong in some cases. So let's consider this optimization function, this loss function. So we wanted to optimize the function at this kind of form, So this is the objective function we wanted to optimize. And the right-hand side is the explicit formula for the gradient. Okay, and we can plot, because like for this optimization problem, we can, it's very simple. It's like a toy example. We can directly plot, or we can directly scratch down the figure between the gradient and the relative loss. So in the figure, we see that the gradient saturates when the relative loss tends to infinity, right? We can see that it will saturated by 0.25, right? That's the saturation value. But as I mentioned, in the developed K-infinity PL condition, it should be unbounded when the relative loss, loss tends to infinite, right? So therefore, for this kind of a problem, it can't satisfy the K-infinity PL condition. Or in other words, K-infinity PL condition is sometimes too strong to be satisfied, right? Therefore, we should develop new conditions to relax the K-infinity PL condition. So that's the motivation of KPL condition. Okay, so for KPL condition, we still have this kind of relation, right? So here the gradient should dominate the loss function by some alpha function, right? This alpha is some function. But here we only require alpha is a K function, which means that it is 0 as 0 and strictly increasing. It can be unbounded, right? Therefore, it is a relax of the K-infinity PL condition. So if this kind of PL condition satisfied, we find that the algorithm, the gradient algorithm is a small disturbance ISS. So in other words, the noise should be, under this scenario, noise should be bounded by this threshold. If noise is smaller than this threshold, we can still have a very good robustness property, which is named the which like tells us about the asymptotic stability of the algorithm and the robustness of algorithm, right? Or like in other words, if noise is smaller than this threshold, the gradient algorithm can still converge to the optimality asymptotically, but under the influence of noise, it will converge to a neighborhood of the optimality. Of course, the size of the neighborhood depends on the magnitude of the noise. Okay, so that's another relation of the PL condition to the KPL condition. Okay. So moving along this line, we can relax the PL condition again. So in the KPL condition, we should require the monotonicity of the alpha function, right? So for the PDPL condition, alpha is only required to be positive definite, right? So it means that it is 0 at 0 and positive when the relative loss is larger or equal to, is like non-zero. It's larger than 0, right? Of course, under this scenario, we can ensure the integral input to stay stable, which means that the gradient algorithm will converge to the neighborhood of the optimality, and the size of the neighborhood depends on the energy-like function of the noise. That's the idea of integral input to state stability. Okay. So now we introduce the framework of PL condition and input to state stability to analyze robustness of the algorithm, right? So now let's apply the developed framework to the different kinds of problem, right? So for this problem, we consider the policy optimization of the LQR problem. Okay, I think LQR is very classic, right? We wanted to minimize we wanted to design a controller K such as the state of the system will be driven to 0 as soon as possible, but with less energy, right? This term denotes the energy term, right? Denotes the energy of the inputs. So here we would like to choose a function, choose a feedback in K, right? So K is our feedback in. And here S is the stabilizing, the set of the stabilizing feedback gains, right? Or in other words, it is the favorable sets for our problem, right? Of course, this is a kind of optimization problem, right? Because the decision variable is K, and the loss function is follows the linear quadratic loss function. Okay. And we wanted to study the policy gradient algorithm under the influence of noise, right? So here K will move along the gradient descent direction, but at the same time, it is influenced by the noise delta, right? And in this paper, we show that the LQR cost satisfying the KPL condition, or in other words, the gradient dominates the relative loss by a saturated alpha function. So here we can say alpha function is kind of this form. So A, B are all constant. We find that for this function, it is strictly increasing, and it will saturate it when R tends to infinite. And therefore, it satisfies the KPL condition, right? If it satisfies the KPL condition based on the results we talked about in the last few slides, we will see that the policy gradient algorithm for the actual problem is indeed a small disturbance as a small disturbance input to stay stable. Here I wanted to note that our results is the first global PL estimate. Of course, this problem is very classic, and recently, due to the emergence of reinforcement learning algorithm, it is studied by many researchers, including the USC group and Polyak in around 2021. So in their results, they only can imply integral as SS. But in our results, we can establish a global PL estimate, and we can show that the system is a ISS globally. Sorry, small disturbance ISS globally. Okay. And we also analyzed other kind of policy gradient algorithm. So the second one is natural policy gradient, which means that the gradient or the decision variable will moving along the natural gradient, or the gradient calculated over the Riemannian manifold. For this kind of gradient system, it's still like we showed that this kind of gradient system is still small disturbance input to stay stable. And of course, we can also show the policy gradient algorithm by the Newton's method, right? So for Newton's method, we should move the decision variable K along the Newton's gradient descent direction. Of course, if there is no noise, we should add additional noise term delta. Here I wanted to mention that the classic policy iteration algorithm is a special case of Newton's policy gradient algorithm. And we show that all these kinds of algorithms are small disturbance LSS under the influence of the perturbations. Okay. So that's what we have discussed in the first part of our talk. So in our first part, we would like to analyze the gradient descent algorithm under the influence of noise, right? Of course, our framework is within the concept of input to state stability. And we wanted to generalize the PL condition, the classic PL condition, to various nonlinear version PL condition, right? And for different kinds of PL condition, it will result in different kinds of robustness, right? For example, if K function, if alpha is a K infinity function, then we can ensure input to state stability. If alpha is a K function, it is small disturbance ISS. If alpha is just a positive definite function, it is integral ISS. And we also extend this idea to the stochastic scenario. So now for the stochastic scenario, the gradient flow becomes a Langevin diffusion, right? Here we can see this is the drift field by the gradient, right? And we should have another term, which is the diffusion field. This is the diffusion field. And here sigma is the covariance of the noise. And third B is the Brownian motion. Of course, like the larger the intensity of the noise, so which means that the lower likelihood we converge to the neighborhood of the optimality, right? Of course, we can see that if delta is equal to 0, right? If like sigma is equal to 0, we can still ensure it becomes a deterministic system, right? We can still ensure the convergence of the gradient flow. But under the influence of non-zero Brownian motion, we can ensure that the system will converge to the optimality with high, with a very high probability. That's the influence of the stochastic Brownian motion. Of course, if different kinds of PL conditions satisfied, we can have different kinds of robustness under stochastic noise, right? So because stochastic noise is often unbounded, so we can't use the deterministic input to state stability. We have to use a new idea which named the noise to state stability. So if K infinity function is satisfied, it is a noise to stay stable. If KPL condition is satisfied, then the gradient system is a small covariance noise to stay stable. And if PDPL condition is satisfied, the gradient flow is the integral noise to stay stable. Okay, and we also apply this framework to the policy optimization problem of the dynamic game, right? So in dynamic game, there are two players. The first player is the minimizer, the second player is the maximizer. So here we show that for this kind of dynamic game, we should develop some dual loop algorithm to find the equilibrium or Nash equilibrium of this game. And we find that the dual loop algorithm is still small disturbance input to stay stable in the presence of the noise. Okay, so that's the first part of my talk. So next, due to the time limitation, I'll briefly go through the learning for control, a data-driven design approach, right? So how can we design the learning algorithm, a learning-based control algorithm such that the controller can directly learn from data without the model, right? Okay, so basically, so firstly, we develop learning algorithm for time delay system. So you can see different from linear system, there is additional term. This is introduced by the time delay effects. So even though we add this simple term, the system becomes like the optimal control problem for this problem becomes super challenging. Because firstly, if there is no delay, we know that we can directly show this problem by showing an algebraic Cartesian equation, right? But after adding this time delay, the system becomes infinite dimensional, and the Riccati equation becomes a set of differential equations. Even model is known to us, it's very challenging to show these differential equations. So here we propose some learning-based algorithm named the policy iteration and value iteration to directly learn the optimal controller. And we also extend the idea to the learning-based control for output feedback system, right? We have similar linear quadratic cost, but we can only get access to the output instead of state. So here we develop some learning algorithm for this kind of output feedback systems. And next, I want to introduce some applications of data-driven control. So the first application is the car following problem. So here we wanted to develop some autonomous vehicles to increase the road throughput and improve safety and save energy of the vehicles. So usually in order to drive a car autonomously, we should consider two directions. The first is longitudinal direction, which means that the autonomous vehicle should keep a desired safe distance from the preceding vehicle, right? And another direction is lateral direction, which means that the autonomous vehicle should follow the reference path, right? Or it can't move outside of the lane. Of course, like for longitudinal and lateral control, there are different methods, but the challenge is that the first challenge is the lane detection problem. So usually they should require the detection equipments for the lane, right? Lane detection equipments. But usually, for example, if a vehicle is driving over a very bad condition road, or even a vehicle is driving over some snow-covered road, it's very hard for us to detect the lane. And secondly, like for a vehicle, there is a coupling effect between longitudinal and lateral direction. How can we consider this? And secondly, like for a vehicle, usually its dynamics is very hard to obtain. So how can we develop learning-based algorithm that combines longitudinal control and lateral control without the lean detection technique. So here, our idea is to directly follow the preceding vehicle. So you can see we can follow the preceding vehicle, but if the preceding vehicle is directly followed by the follower, we find that there are some cutting edge problem, and therefore we should follow a virtual point. So this is like the follower or the following vehicle. It should further follow the virtual point instead of directly follow the preceding vehicle. If so, we can ensure that the vehicle is moving within the lane all the time. And secondly, we use a reinforcement learning algorithm to develop the controller such that it can track this virtual point, right? Of course, okay. So now that's like a workflow of a learning algorithm design. So firstly, we should choose the state, right? The state of the following vehicle should include the position, yaw, velocity, yaw rate, and the side slip angle. And the input of the vehicle is acceleration and the steering angle. So that's the dynamics of following vehicle. And we would like to design the controller such as the tracking error, right? This is tracking error for the virtual point. So that's a tracking error dynamics. We should design the controller such as the tracking error and the control input can be minimized to improve the performance and minimize the energy consumption, right? So here we develop the learning policy iteration algorithm to learn the optimal controller. So here, like different from classic reinforcement learning algorithm, here we consider the model of physics of the vehicle. And therefore, we can ensure that the algorithm is asymptotically, like the controller learned by the proposed learning algorithm is asymptotically, global asymptotically stable, and the convergence of the value function or the value function is monotonically decreasing, which implies that our performance is better and better. Okay. So that's the development of data-driven policy iteration. So that's the result of the learning-based controller. So the red vehicle is a like leading vehicle, and the blue one is the autonomous vehicle or the following vehicle. So we can see the follower will follow the leading vehicle very closely, but keep a very safe distance, right? And we can also extend this idea to multiple vehicles, right? So here we can see there are 3 followers, right? And these vehicles are following the preceding vehicle. And we can see that these autonomous vehicles can still keep a safe distance from the preceding vehicle and at the same time keep the lane, right? It will stay in the lane, okay. And we also extend the idea of learning-based control to robotics. For example, we developed this kind of like wheeled bipedal robots. So there is a wheel attached to the body of the robot. And of course, for this kind of robot, it can operate under different kinds of mode. For example, the general mode or the energy saving mode, which means that the height of the robot can change, right? Of course, there is a second tail, which can serve as a 3-wheeled mode. And finally, we can mount some manipulators on the top of the robots. And here our task is to design the torque applying to the wheel such that the robot can be balanced, right? So for this kind of task, we design the state, including pitch angle, angular velocity, and longitudinal velocity. And then we define the quadratic performance index. And then we propose some data-driven value iteration algorithm to directly learn the optimal controller for this kind of system. Of course, this is data-driven algorithm. We should require the data from the system. And here are some results of the data-driven controller. So the first result is standing up, and second is rotating. We can see that robot is balanced very well by the learning-based controller. And the robot can still be balanced well when it is moving along some curves. And finally, like in this scenario, we can see that the robot is balancing itself when its height is changing to pass through these cones, right? And finally, when there are someone who is kicking the robot, right? Under the external disturbance, it can still be balanced well. And when robot is moving through some speed bump, it can still be balanced well. Okay. And we also, by combining learning-based control with the whole body control, we can also achieve more complex tasks. For example, here we not just balance the robot, but also balance the ball. So here this ball is on the top of the robot, right? If the control performance is not good enough, we know that this iron ball will fall out of the robot, right? And we can also balance the ball, like if the material of the ball is changed, right? Changed from iron to the wood. So that's a comparison between like our controller with the PID control, yes. Or we can also balance the basketball, right? Here, yeah. And we can also balance the ball when robot is moving along some curves. And finally, we can another scenario is that when robot is moving over some obstacles or over some slopes, the ball can still be balanced well. Okay, so we also explore some like more other experiment scenarios. For example, obstacle passing through obstacles, or even like jumping over a rope, and even like jumping over some platform, and even like when robot is moving downwards through the stairs, and for some somersault. That's like the learning-based control and the whole body control together. Yeah. Okay, so we also started reinforcement learning algorithm as a theory of human-centered motor control. And due to the time limitation, so here I will end my presentation. So in today's presentation, so theoretically, we started the robustness analysis of the gradient learning algorithm, and we consider the dual loop policy optimization algorithm for the zero-sum dynamic game, and we consider the learning-based control for output feedback systems and learning-based control for time delay systems. So in terms of applications, we talked about car following control, balance control for wheeled-like robots, and human-centered motor control. So that's it. Thank you for attending. So let me know if you have any questions so that we can discuss.
Thank you, Leilei, for the great talk. I will enable the mic of the attendants so they can just unmute themselves and ask questions. I think now you can unmute yourself if you have questions. Feel free to ask our speakers. Any questions from the audience, also offline audience? Yeah, Mohammed, please go ahead.
So let me drop my raised hand. Okay. Thanks for your presentation, Leilei. It was quite interesting, really nice results. I had a quick question. It's out of my curiosity. When you are proposing or defining three types of conditions, one was like ISS with some small disturbance, and the other one was like with integral ISS. I'm wondering about the restrictive, how first the implication, the final result, and also how much they are restrictive in practice.
Okay, restrictive in practice, right?
Yeah,
okay.
Because one is, I guess, more general than the other one. And of course, there is no free lunch.
Okay, yes. So here, I think restrictive, here we should assume that there is a global, so maybe we can go back to see the PL condition, right?
Yeah.
Yeah, we try our best to generalize the classic PL condition, but maybe for restrictive, there are still other, for example, here we can see that alpha, right? So if there are some local minima, for example, other stationary point, right? So we can see that this kind of condition can't be satisfied. So that's another restrictive or like drawbacks of this kind of, yeah. So for example, if there is a point where the gradient is equal to 0, right? Left-hand side gradient equal to 0, right-hand side it is non-zero, right? Relative loss is non-zero. Therefore, this kind of PL condition can't be satisfied, and we can't utilize to analyze the results globally. Like if there are multiple stationary points, maybe we should analyze the robustness locally, right? Yeah, maybe that's like one restriction. Yeah.
Thanks a lot. Thank you.
Thank you for your excellent questions.
Any other questions from the audience? Feel free to unmute yourself. Okay, maybe I can add one, Leilei, about because you mentioned you extended your result to the stochastic setting with Brownian motions, right?
Yes.
I'm wondering because normally in this machine learning organization, they use this stochastic gradient descent where they estimate the gradient using a subset of data, of course. But do you think this Brownian motion setting cover that case?
Yes, of course. Yeah, I think you are right. So here usually we for stochastic gradient method or for the batch or mini batch gradient method, usually we should introduce stochastic noise, right? So here I think this is also can solve this kind of problem, because if sampling is stochastic, so of course noise should also be stochastic, right?
Okay, great.
Yeah.
And then maybe a second question is about the robotics application, because you mentioned you have this data-driven controller, but then you showed a lot of wonderful tasks achieved by robotics. So I'm wondering what's the role of the learning-based controller? Is it a tracking controller? Do you need an additional planner for that, for all the tasks you have shown?
Oh, yeah, that's a very excellent question. So here, for the learning-based control, our role is for the balancing, because balancing is a fundamental function for the bipedal robots, right?
Yeah.
So for example, so here balancing including the balancing of the body, right? Or even when there are balls, so there are another problem with balancing for the balls, right? So these are these are achieved by the learning-based control. Of course, later we see that there are many fancy somersault or even jumping, something like that. There are a planner part.
Okay.
So we incorporate planning, robotic control, and learning to achieve this more complex tasks.
Yeah. Yeah, thank you for your answer. I think given the time, I think we will conclude. Let's thank Leilei again. I think he started 8 o'clock in the morning there, so thank him for the flexibility to do a presentation according to the Dutch time.
Okay.
Leilei,
Also,
we keep in touch.
Yeah. Also, thank you again for your attending, and thank you, Shenling, for your invitation. Yeah.
Okay.
So
Bye.
keep in touch later. Bye.
Bye.
Thank you.
Yeah, you're welcome. So, is it